So I'm Alexandre Stopin. I'm indeed a project lead for BRGM. I have had the pleasure and the honor to lead the tech project for BRGM for the last 1 year and a half. I think it's very important to first remember what a geothermal reservoir is in the context of the Caribbean volcanic island context. Most often, it is actually characterized by a heat source, which is at depth, so basically your volcano, on top of which there is a reservoir, and that reservoir is the rock that contains pressured fluid more than 100 degrees, well, not more than 100 degrees, sorry. This reservoir is itself under a layer which is of altered rocks, altered by geothermal fluids, and they become clay. They become like clay, if you want, and they act as a cover that keeps the geothermal fluid under pressure and under high temperature. The realization of a geothermal power plants project requires to find such a geothermal system. And the big question is basically, how do you find such a system? How do you characterize them? And also, what do you do if there is not enough heat for power generation? And that's basically what I'm going to discuss today. And that was basically the subject of the work that BRGM did for the project. The first phase of exploration for geothermal system is searching for favorable surface clues like fractured areas, hot spring, gas fumes, hot soils, or altered soils, using surface geology studies as well as geochemical studies. For example, water geochemistry. This technique, water geochemistry, consists in studying the chemical and isotopic compositions of fluid to determine the natures and origins. By collecting information about the rocks and gases which they have interacted with in the subsoils and assessing the potential risks of deposit in wells, which is also very important. So during a geothermal explorations, what we do is to take water samples from hot springs and drillings if we have them. And one of the main applications of geochemistry is the assessments of the water temperature in the deep reservoirs from their chemical compositions. And in particular, what we look for is the concentrations ratio of specific elements such as sodium, potassium, potassium, magnesiums, or sodium, lithium. And these are commonly known as geochemical or chemical geothermometers. And depending on the chemical equilibrium reactions between this water and the reservoir rocks, they give you information about the temperatures in the rocks. The main objective of the study carried out within the ETC project was to determine or even develop the most suitable chemical geothermometers for geothermal explorations in the Caribbean environment, to validate the temperature estimates of deep geothermal reservoirs and to reduce their uncertainties. And that can be significant. Indeed, you can find with other methods something that looks like a geothermal reservoirs, but thanks to geochemistry, you might actually find its temperature. To achieve this objective, what was necessary is to make, for the first time ever, because it was not done before that, we did an extensive bibliographical review of all the geochemical data of the geothermal fluids from all the geothermal wells and some selected thermal springs in all the Caribbean islands for which we had data. And then we compare them and discuss their geochemical composition. That was done for the first time in this area. To complement that, an additional campaign of on-site water sampling and measurement was carried out in June 2022 on the thermal springs of Martinique to complete the existing analytical results. The geochemical analysis carried out by BRGM and the University of the Antilles have confirmed the strong influence of seawater input on the chemical composition of the majority of these waters, which has also been observed on geothermal wells of most of the deep wells of the Caribbean islands. The main findings that this work has made possible is to show that in the current state of knowledge, sodium, lithium, and potassium strontium chemical geothermometers, as well as isotopic analysis of lithium, can be considered as efficient prospecting tools to reduce temperature estimation uncertainties of the geothermal reservoirs on the volcanic islands of the Caribbean. There are other geothermometers, such as sodium rubidiums or sodium cesium, that could potentially be useful in this context. But for that, I think we need more analytical data to see that. So here on these pictures, what you can see is the different measurements, different concentrations, for example, here of sodium lithium as a functions of the temperature. And you can see that basically a geothermal is trying to find the temperatures and the concentration of the different elements, and to draw such regressions. And depending on the composition, that will give you basically the temperature of your reservoir. That's a major finding of this study. Now let's have a look at the geophysics. Geophysics is the study of the Earth using physics. There are many geophysical methods, each of them sensitive to different subsurface properties. For instance, seismic methods makes it possible to recognize different mechanical properties on the Earth related to different geological layers or layers with different stiffness. Something hot may be less stiff than something warm than something cold. You can also use electromagnetic data, which will provide information on the conductivity of the subsurface, which makes it possible to recognize a reservoir containing hot fluid or areas which have been altered by geothermal fluids. The three layers of a geothermal reservoir that I showed before have different resistivity. You can see that the heat source is not much resistive, whereas the reservoir is resistive, and the sealing clay cap is less resistive than a reservoir. The fact that these different layers have distinct electrical resistance makes it possible to detect them with electromagnetic methods. Within the framework of the ETC project, BRGM used these methods, the seismic and electromagnetic, and adapted them to the specificities of the Caribbean islands, and in particular to the proximity of urbanized area, the high topography of the islands, and also the sea. The originality of the BRGM approach is due on one hand to the use of simultaneous deployment in terrestrial onshore and marine environment offshore of electric and magnetic field sensor, and on the other hand, to the joint use of passive and active methods. This combination makes it possible to obtain a 3D image of the electrical properties of the subsurface from land to the sea. During the ETC project, a first geophysical campaign took place on the municipality of Bouillante in Guadeloupe, where we have the only geothermal power plant of the Caribbean. And the objective basically was to validate in a known area the added value of the new methods developed compared to conventional approaches, and also to determine the extension of the field of Bouillante at sea, which was not possible with the old methods and the old data. Additionally, in 2022, another campaign. Hello? In 2022, another campaign.
En même temps. Donc il faudrait peut-être que vous accordiez, mais une seule personne pour traduire, ce serait meilleur que deux en même temps.
Okay, I continue. In 2022, another campaign took place in Saint-Vincent and the Grenadines with the support of the government of St. Vincent. The objective was to improve knowledge on the island subsurface for future geothermal exploration using an innovative combination of passive seismic and magnetotelluric data.
On a une traduction en anglais, alors qu'on voulait une traduction en français, s'il vous plaît.
What I'm showing here on this picture is the results of the two studies. The first one, the first image on the left, shows the results of the inversions of the electromagnetic data that were acquired in the campaign in Bouillante. What we see is the resistivity model under Bouillante. And the good thing is, the very important aspect here is that the image is continuous from land to sea, which is a first and was enabled by the innovative acquisition design, but also the algorithmic development made to handle the strong sea and land contrast and the high topography. A continuous potential reservoir complex with the seal, which is the low resistivity that you can see here, extending away from land, can be seen on the image. And here you can see the wells of the Bouillante power plant. On the right, what we show is a preliminary result of the inversion of the passive data acquired in St. Vincent and the Grenadines in 2022. Each picture shows a different frequency. So here 0.3 Hertz, 0.5 Hertz of the seismic data. And that means basically a different depth of investigation. So here we are deeper, here we are shallower. What we can observe is a slower anomaly that's on the north of the island compared to the south of the island is basically probably related to the active volcanoes that we have on the north. What we'd like to do next is to combine the empty data results together with the seismic velocity and do a 3D inversions to refine the results that we see on these pictures. Now, finally, geothermal can be used for power generations, but shallow systems, as was discussed before by Philippe, can also use the aquifer that can be used for cooling. However, in the Caribbean, this is not necessarily possible as the underground water is too warm for an efficient use of heat pumps to cool buildings. So the question is therefore, can we use the heat from geothermal fluid to generate cold? The study that was led by BRGM showed that yes, it is possible to actually use so-called sorption machine that uses the energy in the geothermal fluid to generate cold. And what I show here on the right is basically a scheme of such a system where the heat from the geothermal fluid is used by the sorption machine here. For this to work, the geothermal fluid needs to be at a temperature between 80 and 110 degrees, which is actually quite realistic. We studied the case of a high cooling demand for a hotel building, considering different scenarios, accounting for different technical environment, economical situations, and different scenarios. The result of the study shows that such a system can definitely deliver the cooling required for such a hotel, and that these systems are economical, provided that the subsidies for non-emitted carbon can be used. Overall, what I've done with this presentation is to show you all the work that was done by BRGM under the work package 4 for geothermal. So trying to find improving technologies to find geothermal, but also trying to find ways to generate cold using geothermal fluid. So I'd like to thank you for your attention. And if you want to know more, the reports are going to be available on the Interreg Tech projects. And feel free to contact me if you want to have more details on this project. Thank you for your attention.